the extract of dissolved oxygen. So dissolved oxygen may reach also to zero. Right? That is what it is showing. Which might not be the case for see, this one is actually not our case. It is a so it is approximately with the leading stomach. Okay, so that is so there, but this one is not that severe. This thing in case of oligotrophy. That we can say, of course, there is some decrease, but the decrease is not that much in case of oligotrophy. Alright? And if it is like a these tropical lakes are there, tropical lakes, the temperature variation not that much. So the thermal stratification that is becomes like a fixed. So over the year, they do not experience the degree of seasonal variation, and which allows the lakes to overturn, and therefore it leads to the generation of many toxic gases. Alright. So this was the UV effect on that, and the thermal stratification effect on the river. The next one is that the effect of acid rain on lake. Right. So you know that the pH level, when it is decreases, then it becomes acidic, right? And acidic, and that acidic lake, if it is pH drops below 5 there, then there are these aquatic organisms are there which can be sensitive to that level, and that might be difficult for them to survive. So this bicarbonate, this buffering, this is one natural way to mitigate the problem of the acid. And you can see that H2CO3, which is acidic, but it's a very light acid. However, like this you can see both side is given. So this break can do and form bicarbonate. So means that the bicarbonate means the acid means what is hydrogen adding, right? We are adding hydrogen to ions are there. So there's this H plus HCO3 can work as a buffer and form H2CO3, which is a very light acid, very light acid. Right? Okay. So that is what you can see that bicarbonate links are there. And this is the HCO3 level. And as you are adding more and more H plus ions, then if there is no other supply of the bicarbonate, it means that you are actually taking the bicarbonate reserve, and up to some level, this is not an acid lake, but this is giving the buffering, required buffering, and that helping it to make it like a neutral. If there is no other supply of the bicarbonate, then it certainly drops. You can see that HCO3 that is dropping because extra H by the acid rain is getting added here, and therefore gradually it becomes acid. If there is no other supply, H plus supply is there, but what is the supply of HCO3? HCO3 is supplied only whatever was present in the lake. So therefore, here comes the importance of the local watershed. So local watershed means that whatever the demography on this, if it is like this kind of hilly area there, from there, of course, there is a runoff chances are very high, right? But there is a carbonate rocks are there, from where this water is actually coming in, and they can add the limestone to the water. This limestone, when it is added to the water, this is also adding the bicarbonate to the water. Means that you are actually adding more bicarbonate, and your acid rain, that is by the runoff, by direct rain, everything is there, but you are adding this bicarbonate there, and that helps out to keep that lake in this bicarbonate lake. Alright? Okay. Okay. So let us now what the discussions are up to now. discussed the surface water, right? Surface water. So the river, what was there, and these lakes, what is difference in the lakes, which is static there, right? So now let us discuss the groundwater and the groundwater pollution. Groundwater pollution we discussed earlier. If there is a on the surface, of course on the pollution from the anthropogenic reason, all are from the above the ground. Okay, but these things can actually sifts into the groundwater and can pollute the groundwater, and as well as if there is this VOC, because the volatile this organic compounds in there, if that goes in there, then there is a evaporation is not possible in the groundwater. So therefore, their contamination is actually very high. Okay. So first, let us discuss. First, let us introduce what is the groundwater, or more precisely, what is aquifers, which contains this groundwater, right? So you can see there is this simple picture which is shown here. This is the surface here. Then after that, immediately beneath the surface, there is this voids are there. Not much there. So these voids are filled with some water, some air. These are there. And from there, of course, it seeps water from the top. It seeps. Right, there is somewhere that you can see that recharge, that station which is showing a recharge area. So it seeps there. Of course, this is the water from there. Whatever the waters are there, your roots they are taking. But you can see that our trees they will depend on the rain, right? It is arid, there is no rain. Then their area also becomes arid, right? So from the outside, externally, we have to supply water. So they actually depend on this rain, etc. Right? But whatever the rains or whatever shifts to there, they can take it from here. Then, when it goes to the more area, so this saturated zone is that the voids are something like that. It is all the voids are right filled with water, completely water, right? Filled with water. So here no air are there. So it is the position from there it is possible to pump it out, right? Easily you can pump it out. Water. There is more water are there. So that is the zone. That's why you have to dig very deep to the well. Right? So that is the point. Saturated water and the saturated zone and the water that remains, that is called the groundwater, and the unsaturated zone it is called this bodies water, right? And after that it is a very solid rock beds are there, and that becomes your confining bed, which is confining the groundwater, and depends upon the demography, the slope, the groundwater flows in one direction. Okay, that is what you can see in that this next river. The few of the things are here leveled, right? So this one is called that filled with groundwater is called the aquifer, right? And you can see that there is two aquifer. One is unconfined aquifer, and there is it is possible that this aquifer can be sandwiched between two rock beds, and this is called a confined aquifer. And you can see that for the confined aquifer, this is your recharge area. Okay, the top level of the groundwater, it is called the this water table, and also the topmost level, it is called this piezometric surface, right? Piezometric surface. So therefore, if your this demographic is like that if your local the height of this land, which is lower than the piezometric surface, then as soon as you dig a well, there is this water will come out, right? So it is called the flowing artesian well, right? You see that flowing artesian well. And if not, then it is in general called this is artificial well, right? We do this your you can see that because of this water this property this comes from this, and that is what you can see it, right? That it is there. Then after that is with the well, when you dig it actually from the see it is digged up to the confined aquifer, and you can see that the confined aquifer then the water actually then overnight you can see that next day that water comes out to the top, right? So that is the your artesian well. Okay. Now how to define that how much volume of the water is available to you, right? So this one is given by porosity, which is giving you the like exact volume of the water that is present. So means that how much is the what is the void subject, right? So that's why it is defined as ratio of the volume of the voids by the and the total volume of the solids and the voids, right? So means that much whatever the water is there, that much you can actually take it out. However, the full water, that is you cannot recover by pumping them. There is surface tensions of these waters are there. So on the rock face, you can see there is like a big space is there, right? So in the rock, this rock surface and the other surfaces are there. Some water will be actually there which cannot be taken out. So therefore, that is given by the specific here. And you can understand that it depends upon that your the nature of the aquifer, right? So if the material is a clay, then you can porosity is very high, but your specific yield is very low, right? Whereas you can see that is your the sand or the gravels, there the porosity is relatively lower, but your recovery is much higher, right? Recovery means the actual water that you can take it out is much higher, 25%, 22% like that. Okay. So this can give you a better idea. This table 11 is that I took it from a Gilbert master. It represents this table. So that if there is an aquifer of sand, then what volume of the water will be stored in a saturated column with a cross-sectional area equal to 1 meter square and depth 2 meters, right? So 2 meter into 1.1, that gives you the volume, total volume. So means that it is the volume of the solids and the voids. And for the sand, you know that the 34%, right? 34% is the porosity, 25% is the specific yield. So therefore, that your volume of the water that is stored there, it is a 0.34 into 2, right? 0.68 meters cube. However, how much water could be extracted from that volume? So that amount that could actually be removed would be your, that would be the specific yield into the volume of the water, right? Not the volume of the material, not the volume of the water. Keep it in mind, that is the mistake in generally done, that it's not exactly the volume of the water, but the volume of the total volume of the material. That is given by that specific yield. Right, so this gives you the idea for a given given that nature of the solid, how much water you can recover. Then after that, the next thing comes that the movement of the groundwater. So which is given by, for that you have to find out what is the hydraulic gradient, right? So the water slope of the water table. Okay. So in a two-dimensional is regard, right? We have you understand why we will understand a little later. I'm saying that it is like a what is lateral cross section I have taken, right? Lateral cross section. From there, I am seeing that this is your groundwater flow is on this direction. Now, of course, that you understand that from the bigger head to the lower head, it will go, right? Where the gradient, opposite of the gradient, like a simple diffusion slope, right? Fine. So how the hydraulic gradient, more precisely, is defined. So that this heads, right, water heads, it is defined with some reference plane. You can see that this data plane, which is a sea surface. Okay, so in general that you can take as a sea surface, and with the sea surface at this position, what is the head of the or height of the water table, right? So that you can measure how. You can just measure that what is the your sea plane, this one, and with some well that can be digged, and you can see that what is the water level there, and this the height that you can subtract, and from there you can find out h. Okay. Then there is another well is there. From there you can see that how it is giving you that what is the head of the water table. And then you can subtract and you can find out that what is the hydraulic gradient. Okay, H2 minus H1 by L, and you can represent it by dH by dl. Of course, you can understand that well, that distance is like a few meters. Okay, not like a kilometer, so not cannot be like a centimeters also, right? Okay, so locally within like a few meters, you can differentiations you understand, right? That when you are doing this, it's like always consider like a very short distance. But the groundwater flows in like kilometer by kilometer. Within few meters, and you can local this water hydraulic gradient you can define as a dH by dl by like digging this some well which is even say 50 meters or 100 meters apart also, right? That you can define. Okay. Fine. So now you see that is what I was telling, that the figure what I shown in the last slide is that like a lateral. I think what is called lateral or transverse. This cross sections means that you are cutting like this, right? Then only that is what you have seen it. The groundwater flow, it is showing like that. So groundwater flow. It's not a. You see, it's like asymmetric thing, right? It is flowing from this. It's a vector quantity. That is the. It is flowing from one direction to this direction. So now the thing is that here I am showing it looks like a horizontal. But what is your x and y? That depends upon that. Okay. So this flow, which is from say positive x-axis. Right. So then if you dig well at this say position, this position, then what you will see that all of this well or any positions here or any position here, all of this well will be having a similar or same water head, right? Okay. So this is called the equipotential lines. Okay. So this is called the equipotential lines, and you see that the water head is changing, right? So along the flow, the water head is changing, and the transverse to that, you have all the equipotential lines. Okay. And this is called the string head. Right. So now you need to find out that in which direction groundwater flow, because you cannot see. It is under the ground, right? From the top you cannot see, from the drones etc. you cannot use it, right? So, this is a simple technique which is shown here, using 3 wells to determine the gradient, right? So what you can do that nearby this area, you can dig these 3 wells. One example is shown here, like this, and in between you can dig this another well, right? And what you saw that this one has the highest head. This is having the lowest head, and this one is like having a in between that. Okay, so right. So what you can do now, you can join a line in between, right? Join the line. Now the thing is that it is not like a few kilometers, tens of kilometers apart. It is like a nearby. So the fall is like linear. Okay, so that dh by dl I am saying that but like a linear. So you can divide it like it. You can see that per unit this distance of whatever the fall is there, that is like a equally it is falling. If it is in a 1 meter, how much is the fall? Then it is also falling like that. So you can divide it in an equal section, and you see that where like this is H1, H2, H3. Right, and you can see that where the H2 is coming here, right? So you can see that maybe that the H2 is coming here. Then what you can do, you can draw this. So this is also H2, this is H2. Right? You are not digging any well, right? Digging any well, but just the calculations now you are doing it here. And see that yes. So this one is your equivalent line. Okay? That is your equivalent line, alright? And it means that your flow is along this direction. Right? Therefore, what you can find out, so any well which will be dug here will be H2. This is also H2, and you find out what is the distance in between, and that this water in H2 minus H1L is given by your water, this hydraulic gravity. Okay. All right. So this example which is given it here in the book. Yeah, just so see the techniques. Otherwise, there is nothing ambiguous or anything. So here you can see that two wells are drilled 200 meter apart along an east-west axis, right? So here 30.2, one is having a 30.2 water head, and another is like a 30 meter head, right? Right. So and the third well located 100 meter due south of the east well has a total head of 30.1 meter, right? So what you are seeing that this one is in between this. Okay. So three wells, you can see that which one is having the which one highest. The first thing is that you identify which one is the like a highest and the lowest, right? So you are seeing that this one is like a highest, it is the lowest, and this is in between. So then after that, what you see the highest and the lowest. So highest and the lowest, and you can divide it in a equal with equal lines, and you find out where your 30.1 meter is coming in here. Then you join it. So once you join it, then this becomes your stream lines, right? This is equipotation line, and so your normal to this thing is the stream lines. Then it becomes the simple geometry, right? Simple geometry. Then you find out draw a perpendicular from here to on this line, and find out what is the distance, which is 100 by root 2. Everything else is given, and that's it. 30.1 minus 30 by 100 by root 2 is given is the hydraulic gradient. So this will be like this. Numbers will be like this. Okay. All right. Got it? Okay. Fine. So hydraulic gradient. That why we are finding it out. Why we are finding out that we need to know that what is the flow rate or the flow velocity of the ground water, which is very low, very slow, but we need to find it. So your diffusion, right? Diffusion, right? All the fixed law, all these things are there. So here also same kind of this fixed law actually. That it's called the Darcy's law. That which is means that the flow is proportional to the hydraulic gradient. right? So Darcy's law, that is relates the flow rate of the groundwater to the hydraulic gravity. Okay, fine. So you can see that Q is proportional to dH by dl, but the proportionality constant, it depends upon that. You can define like everywhere in fixed law we define a diffusion coefficient. So here it is a hydraulic conductivity, right? Coefficient of the permeability. Because permeability is the one which allows you to more flow of the groundwater, right? And A is that cross-sectional area through which the groundwater is flowing. Okay. Now there is some these assumptions are there on which that maintain that it can be valid. So the law is for flow through porous media, invalid when water flows through extremely fine grained materials. Right? It can be flow cannot be like maybe there will be some there will be some sink actually, right? Where it is stored that water. That cannot be naturally stored. It breaks down when the flow is turbulent, which may occur in the immediate vicinity of a pump well. Right? So if there is where it is dig there and you are pumping through it there, then there is a turbulence. Right? Pumping is like this force you are applying there, right? So there will be turbulence will be occurring there, right? Near to this pump well, right? So very likely. So it's a kind of like this laminar this flow, not exactly laminar quantity is not used, but kind of this laminar flow is there. From the turbulence there. And only be used when the medium is fully saturated with water. So it is a saturated flow we are using it, right? Right. So there is this depend upon this hydraulic conductivity, which will be just please stop. Or you can go outside. Okay. So this hydraulic conductivity. The function is on what? On which it depends? Depends upon the medium, right? It will depend upon the medium. Okay. So hydraulic conductivity depends upon that. These are the two field can be classified. Like for example, it could be homogeneous, heterogeneous, isotropic, and anisotropic. Got it? Okay. So what is that? Homogeneous? It is a completely everywhere where we are measuring hydraulic conductivity is same. Heterogeneous, it is changing there place to place. Isotropic is that in every direction it is same, right? And isotropic, it depends upon the direction. Alright, so it is possible there. Right, so once you know the flow, which you can calculate, then you can find out that what is this velocity. So the velocity is called this Darcy velocity. So simple like your Darcy velocity is given by volumetric flow, right? Volumetric flow is as well as A into B. And like in last class also these problems we did, right? So A into B, A is that area, this area to which it is flowing. Right. Right. So Darcy velocity is given by this Q by A K dH by dt. However, which means that it's a theoretical velocity of the groundwater which assumes the full cross-sectional area A is available for water to flow. But when you are having your porosity and the specific here, that real groundwater velocity is considerably faster than the Darcy velocity since much of the cross-sectional area is made up of solids, hence the actual area through which all the flow takes place is much smaller, right? So incompressible flow, incompressible nature of the water means that your A is reduced, B is increased, right? So that's why you can see and you can utilize that same thing, and where you can get the data, the same detail from there. there that you can the porosity, from the porosity you can get it, right? So that's the velocity, and you see that porosity which is always lesser than 1, so the real velocity is much higher than the Dusty velocity. Okay, that's it. So few of these things you can, these problems are there, right? It is given there, and the exercise problems are also like similar, right? So see that here. Only thing is that please identify this. Okay. So then what is given in here? So anyway, this is called the average linear velocity. Right? See. So we have a confined aquifer. Confined aquifer, which is a 20 meter thick and has two monitoring wells, which are 500 meter apart along the direction. So that along the directions of the groundwater flow. And your difference in the water level is 2 meter, right? The difference of the piezometric edge. And the hydraulic conductivity is given by 50 meter per day. Understand that? That's why this is 50 meter, the time is 11 that is 50 meter per day. Right? So estimate the rate of flow per meter of the distance perpendicular to the flow. So it is like you have to find out your everything else is given, right? Yeah. It's a 20 meter, right? So 20 meter your aquifer, right? And so the first thing is that this hydraulic gradient, right? So water height decrease is 2 meter and it's a 500 meter apart. So therefore the first thing is that hydraulic gradient you find it out. Then you find it out that what is the so here the thing is that they have taken this width and see, that's why you can define it like that. This per meter of width, volumetric flow per meter of width. So it is not given, but you can take it as like a 1 meter, right? So 1 meter width, right? So 20 meter, 1 meter width, so 20 this one. That gives you the area 20 to 1, and you can define that yes, the volumetric flow which is going through a 1 meter width is given by that. Alright. Now next part which actually gives you indication of the groundwater is pollution and the detection of it, right? So suppose the aquifer has become contaminated upgradient of the two wells, right? So consider the upgradient well as a monitoring well whose purpose is to provide early detection of the approaching plume to help protect the second drinking water well. How long after the monitoring well is contaminated would you expect the drinking water well to be contaminated, right? Understand that means that you are upstream, right? So upstream you understand, you find it out that it becomes contaminated, right? Then naturally you will be trying to see that where this along the direction of the downstream, the groundwater well is flowing, that how long it will take. You understand that it is a point source. With the point or this identify that this is the source from where the pollutant is actually getting richer into the this groundwater. But now you need to find out how long it does it take to reach the level. And there are some troubles there, dispersion, etc. that we'll see later. But right now, at least the first order approximations that can be given, we can use the velocity, the linear velocity to find out how long does it take to reach there, and that another downstream that is a drinking water well is there. So how long it does it take? So if it is still it is not reached there, then in between you can dig a well and take it off. That is how the contamination is taken it off, right? So that's it. Actually, you can find out first the this Darcy velocity, and you see that what is that is you should be having the idea what is the medium that is there in that area, and from there you can find out what is the average linear velocity. You can again see that it is much higher than the Darcy velocity, and the second well is 500 meter apart. So how long does it reach? You can reach say here 2.2. So you have like at least still have enough time. That it is, you can see that it is not still contaminated. So when through there, just this is this early detection is there. Okay. then you can see groundwater moves very slowly. Okay, so this is the what we have not or ignored here, any dispersion or the diffusions of the fluid, right? So dispersion is that, remember that plug flow model means that the contaminations can actually be leaking, right? It can be leaking from them, right? Or it can go in the other direction, and that the diffusions of this like that, that it is there, but it is not plug flow. Here what is we are taking that it is again plug flow, means that the contamination is in the groundwater, and with the groundwater flow that is flowing there. However, it may happen there, right? Because it is very likely, in fact, which happens there, that there is a diffusion. Means that the contaminant is diffusing in that water, and there may be some dispersion in this, dispersion in the calculation. Okay. Right. Anyway, these are the things. I ignore any cooling effect of the groundwater, drinking water. Okay. So, next class we can discuss this.
Present, sir.
Avinashi, Ivan, Deepak, Kirti, Arshi, Salohi, Naina, Bharti, Prabhakar, Rachit, Anushka, Dipanjan, Jaya, Vinayak, Vikash, Ritu, Sehuraman, Mukta, Sailesh, Shubhajit, Harshit Kumar Rai, Prashant Pandey, Abhay Dev, Ankit, Anushka, Ayush Kumar, Vanwadi, Pranjal, Richik, Aditya, Aniket, Harshit, Prabhunath, Vishal Vaibhav, Deepika, Divyanshu, Khushbu, Saurabh, Narendra, Puneet, Shivam, Narvesh, Sanitya, Lohit, Ramalkant, Shashwat, Yashoshi, Hamlet, Mohit, Tushar.